Okay, very good. So let me add a few things to what I said last time. Last time we discussed a mechanism of spontaneous supersymmetry breaking, which is F-term breaking, and that was discussed in a very specific model called the Tata model. Now, in between the last lecture and this one, I happened to be reading Weinberg's textbook, volume 3 of his QFT, and I must say that this person is a real major source of inspiration and does things often in a new way. So I learned a couple of things about what we have done from Weinberg, and I just want to share that with you. One is that there's a very general version of Rafferty model which sort of, I know this is slightly off the point of the course, but it's so pretty that I can't resist telling you, because it explains how the supersymmetry breaking mechanism works, and it also gives us an insight into how to generalize this model. Okay, so if you remember the specific model we discussed last time had a superpotential, it had 3 fields. So we'll also see why it needs 3 fields. And last time we had taken a very specific form where W was phi 2, phi 3 with some coefficient and M, and then with another coefficient lambda. Field was phi 1 to phi 3 square and 3 square. Okay, the general form is take a bunch of fields, superfields, tidal superfields yi, I equals 1 up to n1, and another bunch x, let's say I, capital I equals 1 up to n2. Alright, and write the general superpotential W equals summation over I from 1 to n1 of yi and some arbitrary functions fi of the x's. Alright, the key point being that it's linear in all the y's. Okay, so if you look at this action, phi 2 and phi 1 are like the y's and phi 3 is like the x's. Okay, now what are the F-term equations for supersymmetry to be unbroken? Are the equations dw by dy equals 0, and this is just fi of the x. So we want all the fi of x equals 0, and we also want these to be 0, but these are yi f del fi by del xi. Alright, now we see, so this is for unbroken Suzy. Now we see that the second set of equations are very easy to satisfy. Choose all yi's to be 0. So choose all yi 0. That takes care of all these equations. Okay? That leaves the first set of equations, but how many are there? The first set are n1 equations labeled by small I in n2 variables xi. Right? So how do you make sure that n1 equations in n2 variables don't have a common solution? Just choose n1 greater than n2. Generically that will do it for you. Okay? That explains the Rafferty model where n2 is 1 because there's one phi 3. So you needed 2 fields, phi 1 and phi 2. And if you remember, they gave us the equation phi 3 is 0 and phi 3 squared is mu squared, which are 2 equations in a single phi 3 and they are mutually incompatible. And that's how it worked. Okay? So, this can always be made overdetermined. Okay. So that's one insight which makes this model look much less contrived. The second insight is that this model itself we had a bit of trouble analyzing it because there seemed to be a flat direction with phi 1 and all that. I think it's much simpler to analyze if we change it to Weinberg's version of this. We have this problem with Wenceslas. Lots more clocks, so maybe we can get the fan creates unwanted noise in the video. That's the only problem. But thanks, sir. Okay, so Weinberg suggests a slightly improved version of this model, which I'm just writing down, and then I'll conclude this part of the discussion and go on to today's lecture. In which he says, instead of this, with the same field content, replace it by W equals phi 2 phi 3 minus mu plus lambda phi 1 phi 3 squared. See, it's very simple. All you need is two equations, the phi 2 equation and phi 1 equation being incompatible. So instead of putting the shift term in phi 3 squared, put it in this term. This still works because phi 3 minus mu and phi 3 squared cannot both be 0. But I claim that the analysis of this is much simpler, and I'll leave this as an exercise. Okay, so this is a slightly cleverer version. Maybe your Rafferty's original model was like this because it was found by playing around, but it makes more sense. You can analyze. So the exercise is to analyze this in extreme detail, find the Goldstein, find the mass splitting, find it. It's a few lines exercise. It's what I did last time, but it will be easier in this form. Okay, so that concludes the discussion of F term spontaneous breaking, and the punchline, if you want one, is that in F term breaking, we found that the sum rule is obtained, holds that the super trace of mass square is 0. We actually didn't prove this rule because it only came out as an empirical rule by studying this model. But it's possible to prove it, and we'll prove it in a few minutes. Okay, we'll prove it soon. And from this we concluded that there's a problem implementing this in any physical model such as MSSM, because the super trace of this operator being 0 means that some superpartners, if you make them heavier than the ordinary particles, then other superpartners have to be lighter in order to add up to, on average, to 0. And that means that we'll have some superpartners to be very light in contradiction with experiment. So this is bad news for phenomenology, as I said last time. So how do we improve on this situation? We would think that let's introduce D-term breaking or a combination of D-term and F-term breaking, and let's hope this is better. Okay. So this story holds in a theory exclusively of coupled chiral multiplets. Now we go to a theory of coupled chiral and vector multiplets, which is what the MSSM is after all. And let's try to see whether we have any better shot at supersymmetry breaking from here. Okay. So let's recall what the potential is when you have both F terms and D terms. The scalar potential is simply the square of the F terms plus the square of the D terms, and it's written as summation over I superpotential comma I squared, because remember that Fi was minus Fi star was minus W comma I phi. Likewise, dA, the D term, was G phi dagger dA phi. That's, I think, my notation. And so here we had a Because d terms are real while f terms are complex, we had a half dA dA. So it was a half summation over A of phi dagger dA phi squared. So that's the thing. And it looks pretty complicated because notice that the same fields phi appear here as well as here, but in a somewhat different form. Here it's like a sum over mod squares, and here it's somehow mod squared and then sum. So there's a kind of different form with respect to their complex nature. Okay. And this can be extremely complicated, and it's governed by this function W, which is the superpotential. So that's a free choice of ours. But here it's always quartic, and it's governed by the gauge couplings of these chiral supergroups. So that's not up to us. Okay. Now, yesterday while preparing this lecture, I had a moment of panic when I realized that I had never in my life written down this term explicitly for a field which, let's say, is a triplet of SU3 and a doublet of SU2 and has two different hypercharges. I didn't know how it can be done. So I'm going to waste your time by giving an example. So in this example, I'll take exactly what I said. Phi has an index I and an index I. I goes to 1 from 1 to 2, so it's an SU2 doublet. It's not supposed to be realistic, but it's pretty close to realistic. I equals 1, 2, 3, so it's an SU3 triplet. But let's make matters a little worse. Let's have two types of doublet triplet fields, and for A equals 1, A is 1 and 2 is an additional index, which is a flavor index if you like. And let's do something which is not done in the standard model, which is to give different hypercharge assignments for the two different flavors. So we haven't written the model, we can do whatever we like. So let's give, and let's have two hypercharge groups. I'm making all this very complicated because then when you see how to write the D term, you'll begin to understand what its structure is. So let's have two hypercharge groups, U1 cross U1 prime. It's not so uncommon in supersymmetric models, as well as then SU2 and SU3. So the hypercharges are Y and Y prime. So let's say that phi A has hypercharge Y1 and Y1 prime, and 1A equals 1, and phi A equals 2 has hypercharge Y2 and Y2 prime. So I've given you all the data about phi and its quantum numbers, and now who volunteers to come and write phi dagger dA phi? It's a lot of fun. By the way, I did this in a hurry, so I might even get it wrong, which will make it more fun. But this is what I concluded, and it taught me a little bit about what this means. So my conclusion was that I haven't written it down, so it's a test to see whether I can reproduce this. So there is a term. So what I need to do is write half summation phi dagger dA phi squared in this particular case. So I claim this is a half which is outside everything. Phi. Now here I am going to put, there's a G. So I'll put the SU2 index and the SU3 index. I'll put now the generators of SU2, I, J, star, phi, J. So capital I is contracted diagonally while I and J are contracted by SU2 matrices. Okay, so I claim this is one term, and this should be multiplied by the coupling constant of SU2. Okay, and I square it. Next I add the term G3. This time I put here the D. Unfortunately, I have to keep using A. So this is summation A equals 1 to 3. In the next term, I have summation A equals 1 to 8. dA of SU3. Let's make the notation very clear. j by I j star squared. Okay, so this time the generator of SU3 is contracting, but the other generators are all diagonally contracted. Okay, and then the U1 pieces. First of all, so there will be two pieces. One will be, okay, so sorry, there's another index which I hadn't put. A and A are just summed before squaring. Okay. This time all indices will be just summed because it's U1. But we'll have YA. YA. Good, thank you. Wonderful. Okay, and now there's a little bit of extra fun. Since this is a U1 factor, we are allowed a phi Helioculus parameter. So we can also add eta to this before squaring it. Okay, so this is not exactly this, it's this with almost general phi Helioculus parameters, which are of the form eta times d, where d is the last component, or eta times b, where b is the vector superfield, but only for the U1 vector superfields in the problem. So here's a term, and here there's a sum. So it's eta plus y1 phi star 1 phi 1 plus y2 phi star 2 phi 2. Add them up and then square. The key point why I'm doing all this is so that we learn what has to be added and what has to be then squared. I mean, in what order we have to add and square. And then of course the last term is another independent phi Helioculus parameter for y prime, the second U1, plus y prime a phi star a, otherwise the same structure. That's it. Okay, so I hope this gives you an idea what writing a D term really means. It's all buried in that nice notation. I'll also basically tell you how you can derive this for yourselves. Let's remember where a D term comes from. I'm possibly belaboring a point too much, but since it disturbed me so much, I felt I should pass it on to you. That it can be more, that much more is hidden in the indices than we think. Where it comes from, it's very simple, and in fact once you see that you'll understand. It's phi dagger e to the v phi is the basic coupling, right? Now here we include all the gauge fields V. So there's G2, V2, G3, V3 and G times V, the first U1, and G prime times V prime for the second U1. All are here. But each of these is a matrix in a different space. So the U1 guys are just pure numbers. The SU2 guys matrix in small ij space. The SU3 guys are matrix in capital Ij space. Okay. Where does the contribution to this come from? It comes by taking the last component of V when we expand this. Expanding this looks like a group element because it's E to an algebra element. Expanding it to first order V makes it back to an algebra element. Take the last term, which is d times theta, theta, theta dagger, theta dagger. You've used up all the thetas, so from here and here you only need the scalar pieces, phi star and small phi star and small phi. Okay, and that's it. That's the term. Okay, but then you get one such term for every v, so it's a linear sum over all the v's, and that's why you get such a thing separately. And then each d equation of motion causes this to be squared, and then you have to add this. So this will just do it. Okay. So now we've established how the d terms look, and now the question we have to ask is, what chances do we have? Finding b greater than 0 for this nice general potential coming from the sum of both f terms and d terms. Okay, so are they any better than our chances of finding this guy being positive alone? Now actually finding this guy being positive alone we already discussed last time, and we found that sure it can be done by O'Rafferty models and their generalization. The only limitation is it all works fine, but we get a sum rule which is a little unpleasant, that's all. So So can we do better or can we avoid having a sum rule? Now here, of course, there should have been this phi Heliopolis parameter. So let's put it back. So this is really half summation of A bracket eta A plus this thing, with the understanding that eta A is 0 unless A happens to be one of the abelian factors of the group. So this runs over, if you like, this A in my example goes from independently from 1 to 3 and from 1 to 8 and over y and y prime. So it has 13 values. And for 2 of those values there is an eta, and for the other 11 there is no eta. Okay. So let's take the simplest thing first, analyze without eta. So with all eta A set to 0, and we'll find the very, very surprising and depressing conclusion that we are no better off trying to break supersymmetry in this than we were in the model with only chiral superfields. Or in other words, the theorem which I'll prove for you, that SUSY is broken in spontaneously. This model I mean the thing up here, if and only if it is broken by the F terms alone. In other words, if W is chosen such that this thing spontaneously breaks supersymmetry, then so does this. But if W is chosen so that this preserves supersymmetry, then so does this. The whole thing. Okay. And it's quite bizarre because of course there is no guarantee from this that the phi's which make this 0 are going to be the phi's that make this 0. No reason to think so. But I'll give you the proof of this theorem, which again I learned from Weinberg's book, and it's extraordinarily simple and beautiful. Thank you. G here, GA, and GA again you have to sort of decide. It's G2 for all the, when all the A's run over SU2, then it's G2 when they run over SU3, it's G3, and when they run over U1, U1 prime, then it's 2 independent GY and GY prime. Okay. So proof of this theorem. It uses a very, very lovely property of supersymmetry. So let's prove it in this direction. Suppose W comma I equals 0 is solved. W equals comma equals 0 for all I is solved by some configuration of the phi's, of all the phi's. Okay, so we assume that it has a solution such that all the different phi's can be chosen and we get 0. Okay. Now, this is a gauge theory. Okay, and W is gauge invariant by assumption, and remember it's a potential term. Okay, since W is gauge invariant, the entire orbit e to the I G alpha A T A phi is an equally good, gives equally good energy. This is step 1 of the proof. Is this point clear? I assume there's a configuration of phi's which makes all these W comma I equals 0. So I can, if I gauge transform the whole lot of them, then of course it still makes this thing equal 0. Okay, so for all arbitrary choices of parameter. Okay, so this is step 1 in the proof. Step 2 is rather dramatic. Since W is holomorphic, which means analytic, which means it contains only chiral superfields and not phi daggers, the above is true even if lambda, even if these parameters alpha are complex. Okay, because if I complexify the gauge group, A In general, of course, it means that when phi transforms this way, phi dagger would transform as e to the minus ig alpha star dA, which would not be the inverse of phi. So if our gauge invariance depended on cancellations between phi and phi dagger, then it would fail at this stage. But it doesn't depend on that because W depends only on phi and not phi dagger, the key point of supersymmetry. Therefore, whatever you did to make it gauge invariant, which would have been typically to give different charges to different fields, that formal property will hold even if you complexify the gauge loop. Okay. Now consider the auxiliary quantity it's not part of any action, I just want to consider it for my own fun. Phi dagger phi, which I mean take phi and then dagger and transpose in all the indices and then contract away everything. Okay? Now phi dagger phi is a quantity that's clearly gauge invariant under these gauge transformations very generally, but not under these. Okay? This is invariant under real gauge transformations, under genuine gauge transformations if you like. When I say real, I don't mean the gauge transformation is real, I mean the parameters alpha are real. Gauge transformations, but not complex. I hope it's clear why. Because if this transforms by this kind of matrix, then phi dagger transforms by e to the minus dash, but there is an alpha star, so those fail to cancel, so it's not invariant. Okay. Since it's not invariant, there is an orbit of phi dagger phi under the complexified gauge group. Okay. And since phi dagger phi is positive definite, it must be minimized at some point on this orbit. On the complexified orbit. It's invariant along the real orbit. It varies along the complexified orbit. By the way, it varies, but it never fails to be positive definite because it's always dagger of something trying to itself. Okay? So since it's that, it must be minimized somewhere. So at that, at the minimum, the variation of phi dagger phi must be 0, and this is equal to I alpha A minus alpha A star phi star dA phi. Because the variation of phi gives me I alpha T phi, and the variation of phi dagger gives me minus I alpha star phi T A on the right, phi star. Okay.
Yeah. So since alpha is non-compact now,
yeah,
it could happen, at infinity or something. This minimization could happen, but that probably doesn't matter.
It might happen at infinity. Actually, you're right.
So the phi dagger phi is only sort of bounded below like thing.
Yeah.
And it could sort of run away.
Okay. I don't know if that's a problem. Anyway, but now you see what we've achieved. We've taken a configuration, a vacuum configuration that makes this 0, and we found an orbit of it which continues to always make this 0, and there's some point on that orbit which also makes phi star TA phi 0 and thereby makes this 0. Okay, so we proved our theorem, which is that if the F term conditions are satisfied, we can always make the D term conditions satisfied, but only as long as there is no eta. If there is eta, then life is different. Okay, so it means that the best hope for doing any sort of supersymmetry breaking, spontaneous supersymmetry breaking, possibly violating that super trace law, is to introduce phi Heliopolis parameters. Okay. Unhappily, in the standard model or the MSSM, there is only one phi Heliopolis parameter, but in other supersymmetric models, there can be many, depending how many U1s you have. Okay. By the way, notice that this proof is somehow crucially tied to the origin of D terms as a kind of infinitesimal variation of the original. If you think about superspace gauge invariant actions, this complexified gauge group is really appearing in a way, because we vary by e to the lambda, where lambda is a chiral superfield. So ordinary chiral superfield phi goes to e to the lambda phi, where lambda is complex. And so the complexified gauge group plays a role in this. Not that the entire theory is invariant under that. Okay, the group is sort of present, but it's an invariance of part of the theory and not of another part. Okay, let's not belabor that point too much. Good. So in order to see what happens with the D term, probably the simplest thing is, instead of writing this most general stuff, let's look at one example. Moreover, we'll look at an example where W is 0. So, example, just one chiral superfield. Phi of some charge and coupled to a gauge field, coupled to U1. Now, if phi is coupled to a U1 gauge field, that means it's charged. If it's charged, then there's no superpotential we can write down, not even a mass term. Right? Usual story. Okay. But we can have a D term, and in fact the D term is very easy to figure out what it is. D is just minus of eta plus Q, so coupled to a of charge Q. So Q phi. Yes.
So does this argument make a prediction for the dimension? So suppose I was interested in the dimensionality of solutions to the F term.
Yeah.
F term equations. Where I count on these solutions as distinct if they're not related by genuine relation.
Yes.
So it sounds like you almost have an argument to say that the dimensionality of that manifold must be equal to the dimensionality of the rank of the gauge group. Because for every coupled to every genuine gauge transformation, there's a complex gauge transformation. And you argue that the minima are invariant.
Well, it boils down to how many minima this phi star phi has. Of course, it could have many.
Suppose I'm only interested in D term minima.
Okay.
Just to start. I'm interested in just asking how many minima are there for the F term.
Yes.
So because you found many minima of the F term equation just by using complex gauge transformations, it predicts minimum.
That way, yes, that's right.
Minimum dimensionality.
Yes, that is correct. There is a dimensionality of the minima of the F term,
which is equal to the rank of the
which is equal to the rank of the gauge.
At least.
Yeah.
It could be more, of course.
Yeah. Okay, there's one caveat here perhaps, which is that obviously if the wave turns out to be 0, let's say the F term is minimized by 0, then 0 of course is gauge invariant, so it has no orbital. So I don't know.
Okay, some of these could be anti, right? So it's not true.
So it's
right.
Okay. So here let's look at this example and notice that therefore there is a mass. Okay, so here's the example of a D term, no F term, and there can't be an F term.
Sure, was a question.
I just understand this argument. How do you know that the minimum isn't at the point where alpha is real? I mean, if you set that thing to 0, then it makes the entire orbit.
If I set this thing to 0, it makes the entire
orbit. It makes it in 4 bands.
No, see. No, I
But
cannot
alpha is
understand.
real, the orbit is not changing.
No, alpha is up to me. I can be at any point and I can define the orbit starting from that point. Right?
Differentiating with respect to alpha.
Yeah.
That it's just a phi star TA.
I'm differentiating with respect to im alpha, crucially.
Yeah.
In other words, if I'm at a stationary point of phi dagger phi,
Also, alpha is the infinitesimal.
alpha is now the infinitesimal deviation away from it. Yeah. No longer, it doesn't have to be the one from any preferred, because the point I started with has no preferred meaning anyway. Now I'm measuring alpha from the minimum, and so I make a transformation. Clearly, again, phi dagger phi is necessarily non-invariant under that transformation. the only best it can be is invariant to first order if that point is a well, it could be invariant to a few finite orders if that point is a finite order stationary point. But in particular, being a minimum, it has to be a first order stationary point, and that's all we need. Okay. So here, the superpotential is necessarily 0 in this model. Okay, you can't write down a gauge invariant superpotential for one charged chiral superfield. Good. Now, minimizing the B term is easy. That you just choose phi to be 0, that's clearly the minimum, as long as eta is positive, or at least more precisely, if eta times q is positive. Note that q is real being the charge of phi and eta is real being the phi Heliopolis parameter. Both are necessarily real. Okay. If they are of the same sign, both positive or both negative, it doesn't matter which one because this is going to be square anyway eventually. D is going to be square. Okay. If they are of the same sign, then the least value you can get is phi equals 0. Okay. On the other hand, if they are of opposite signs, then we can minimize it away from 0. And if beta q is less than 0, then choose the wave such that phi, the wave mod square, is minus eta by q. Positive. Notice that in the first case, this is the minimum and SUSY is broken. The vacuum energy is a half eta squared, and eta is a parameter that's up to us. Notice also that the U1 is unbroken because phi was a charged field. If it had got a wave, then U1 would have been broken. In the second case, notice that if I can choose this, then I've managed to make D 0. So in this case, SUSY is unbroken and U1 is broken because phi has to have a non-zero. Now there is not a strict correspondence between these things. It's just important to keep in your mind that the same wave can break either SUSY or gauge invariance or both or neither. So you can see in this very simple example, you can see that it's either or. Okay, so these are phenomenological constraints if you want to look at it that way. Because finally our job is to break both in specific ways. Yeah.
Sorry, I just realized that there was a main correction to the statement I knew before but I hadn't understood. Is this correct? So you've demonstrated that this, in the absence of Heliopolis terms, that the solutions to the vacuum is the solution to the F terms equation modulo complex gauge terms.
Yeah, it's the same statement.
Yes.
So the statement is that the solution to the say that again.
Solutions to the F term equation modulo complex gauge terms
is the solution
to the vacuum.
To the vacuum
of the theory.
Yeah, that's correct. The vacuum space is the solution to the F term equations modulo complex gauge transformations. But I guess
And the key point is the complex you can use to solve the D term equation.
Yeah.
So you never need to talk about D term
That's
equations.
exactly right.
Just mod out the
That's
complex.
exactly right. Yeah. Okay. So in this case, good. So we've got this structure. So let's see what the story is when supersymmetry is broken. So phi takes the wave 0, and we notice that since the superpotential was anyway 0, the fermion is massless. This superfield has a fermion component psi. So the fermion psi in phi is massless. Now I'm talking of this case. No surprise, it's the Goldstino. While the scalar partner of this fermion is phi, and it has a mass term, you can read it off from here, it's eta q. Okay. This fermion has mass m squared equals eta q. Okay, so we see that, and in fact the there's a half which is annoying me slightly. Because it's a half t squared. So it looks like the mass is 8 by 2, but we won't worry about that. Okay, but the exciting thing is, here's a mass splitting which doesn't respect the sum rule. This is the exciting part. Okay, there's a Goldsteino and there's a massive scalar in a theory in which, without supersymmetry breaking, just by tuning parameters the other way, instead, then the fermion would have been massless and the scalar would also have been massless. Okay, so the natural masses are 0. So if a supertrace rule applied, then the supertrace would be 0, which is a little absurd, of course. And in fact, it's not 0. And we see that supertrace of m squared in this case is 2 eta cube. Or another way to say it is that it's minus twice cube the wave of d, because the wave of d is eta, is minus eta around the vacuum phi equals 0. Okay, so finally we've got some violation of the supertrace rule, and we see that it's the phi Heliopolis term which is making this happen, because the wave of d is eta. Got it? Looks good. Now, just in case you get too thrilled by this example, I'll point out to you that it's again an anomalous theory. So it's not a good example at the quantum level. Unfortunately, this theory is anomalous. Well, there's again a chiral fermion. The U1 gauge theory with a chiral fermion. And if we try to repair that, then we are led to something which resembles super QED, which I did some time ago. So you can repair it by introducing two chiral superfields, phi plus phi minus, of charges plus minus q. Okay, and with this, you can have, so your d term now is minus of eta plus q phi plus mod squared minus phi minus mod squared. Okay, now this theory is certainly non-anomalous. Unfortunately, now it doesn't break supersymmetry at all.
So what is the anomaly in the original theory? Which symmetry is anomalous?
Yeah, actually I was just trying to figure that out while saying this.
The rotations of the chiral fermion.
Yeah.
So what? That's it.
Yeah, actually it's not clear that that's a problem. I'm not very convinced about the statements I see on anomalies in the literature. That could probably be made a bit more carefully. Probably what would happen is if we try to embed this, you see, this is just the U1, we're just focusing on the U1 sector of some theory, because the Heliopolis d term was only in that sector. So probably people mean to say, but they don't really say very clearly, that it will be anomalous if we try this kind of field content in a non-abelian theory.
Gauge linear sigma models of this sort in 2 dimensions are anomalous in U1 sense, yet they're perfectly sensible.
Yeah. Okay. Now, if I put two superfields of opposite charges, then this is my d term. But now you see that supersymmetry is never broken, because whatever the sign of eta, we can give a wave to either phi plus or phi minus. Okay, to cancel out eta. If eta is positive, we'll give the wave. If eta is the same sign as q, we'll give a wave to phi minus. If it's the opposite sign, we'll give the wave to phi plus. Either way, we can make this 0. Okay. So, just to show you, I think this conclusion is fairly robust, that if I have pairs of superfields of opposite signs, of opposite charges, which is a very common thing, then it makes it harder to break supersymmetry via D-tubes. So the whole thing is extremely interesting, but it's the moral is somehow that spontaneous supersymmetry breaking not an easy thing to achieve. And it's very constrained. Yes.
I'm sorry to go back to my question of the non-compact thing. So I think
Yeah.
that if the orbit of phi delta phi is non-compact,
Yeah.
then it may not have any minimum at all. It
Yeah.
may not hit zero anywhere for any finite point of the orbit. It may not hit zero. It may not hit any minimum at all. I mean, it might just go.
But the orbit is certainly non-compact.
Yes,
So
then
we are really assuming that it can be minimized. We could compactify it in some sense by adding that point at infinity. So we would say that it takes a minimum somewhere, but it could be at infinity.
In other words, for no value of alphas, do I ever have any minimum? I mean,
yeah, that's okay. But the question then is the same as whether it's okay to consider a minimum where the fields take some kind of infinite expectation value. My case is that by suitable changes of variables, you can often make those things finite. But one would have to look at examples.
I'm saying suppose it's like e to the minus alpha x or something like that.
Yeah.
So it's so for no value of, I mean, there you can't make this
Correct. Correct.
Or delta.
I agree. Okay, so put it another way, we would this conclusion holds only if phi it tells you a way to construct this solution, right? Of course, if it fails, then maybe you can say that's a good model. But given the F term, you would look in the space of complex variations of that F term vacuum.
Yeah.
I think there must be, the fact that the statement is effectively in the mathematics literature means there must be some sense in which it's compactified.
Is there any kind of normalization condition on this phi or something? So that it has
Not usually. Well, yeah, I see. Boundary conditions on phi, maybe. No, not boundary conditions. So you mean on the norm of phi?
Yeah.
Phi. Just take values on the complex. There must be a way in which this can be made sense of, but I can't tell you here what that way is. Anyway, since we are all phenomenologists here. Okay, good. So the last thing I want to do is to consider back to the most general case, consider this case and give you the general mass sums. So the purpose of this will be to show you two things. One, that without these phi Heliopolis parameters, the rule is that the super trace of mass squared is 0. And with them, the rule is that you get something proportional to them on the right side, of which the example I showed you with one superfield is some kind of special case. Okay. So for this, it's a little bit of boring work. So let's take this guy and rewrite it as summation I fi mod square plus half summation a just the same as that. Fi evaluates to that thing and dA evaluates to that thing. Okay. Now let's look for the condition that let's look for the true minimum of this potential. So in particular, this condition should be satisfied. Okay, we want a general mass sum rule which is true regardless whether that minimum is supersymmetry breaking or not breaking. If it is in supersymmetry, it's not supersymmetry breaking, then we know that the rule is satisfied. Now we want to look at the case where it's generically broken. But if it's broken, we still need to find this minimum. And this minimum now can be written in the following way. So del V by del phi I is equal to, let's write this as W comma I, the first derivative of superpotential. So this is W comma Ij, W star comma I, or J perhaps, J. plus dA comma I dA is equal to 0. Okay, so the comma I means differentiation in phi I. In the case of W star, comma J means differentiation in phi J star. Okay. In the case of D, it will be a little more ambiguous because D depends on both phi and phi star. So this particular one means differentiation in phi I, and if it's I star, then I'll put a bar to indicate that. Okay. Now let's evaluate dA comma I just from the basic structure of the D term. Okay. So dA comma I is variation of dA phi I, which pulls out the phi on the right of this and leaves behind G phi dagger dA. So it's G phi dagger dA I. Okay. Then for good measure, also let's consider the derivative of dA in I bar, which by definition is derivative of dA in phi star. And this pulls out the phi star on the left, so it's G dA phi I. Alright. Now, if we consider dA comma I, A is always up, dB comma I bar, and sum over I and I bar, sum over this repeated index, then I get okay. Now my point is that this is closely related to the mass term for gauge fields, and this arises as follows. I mean the mass term for gauge fields after Higgs mechanism. After these files get a wave. Okay, and in fact, if you recall, I did this in my first lecture or second lecture. From the fact that d mu phi I is d mu plus Ig dA Ij delta Ij Yj. If I take d mu phi star d mu phi, then I get so here I take the sorry I left out the A. Right. So if I take this and square it, I get 2 A's and 2 phi's, and I just want to write the structure of that term. And that term is clearly G square phi star dA dB phi mu A. Okay. So now we can compare this with this, and we see that I can recast this gauge field mass term precisely in terms of these. So another way of saying it is that the mass matrix for gauge fields is a matrix in AB space, the mass squared matrix really, and this should have a half because A's are real fields. So I can put a half and also a 2 here, and then what I'll do is I'll symmetrize this side in A and B to make it more manifestly symmetric. So I claim that this is dA I dB I bar plus dA I bar dB I. Is this accepted? So this is one ingredient in our super trace formula. It's the mass of the gauge fields. Post-Higgs mechanism. Okay, everything here on the right side is in terms of waves. We simply assume some structure, unknown structure of waves for the various phi's, which gives some structure of waves to the d's, which gives some mass to the gauge fields. What we'll see in a moment is that all mass matrices can be completely parameterized in terms of d's and f's because they are the basic quantities which get waves in a supersymmetry. Okay, the fundamental quantities getting waves are the phi's; those are the fundamental fields. But it's enough to know the waves only of d and w comma I, and you get everything. So here's part of the story, so let's complete it. The next question is, what's the fermion mass matrix? And for that, first we have to take the fermion matrix MAIJ. Now this is an interesting thing, you may wonder what this means. It's really the matrix defined by having, I mentioned at some stage that fermions and gauginos could mix, okay, and will mix generically. Therefore, the mass matrix for fermions should be a mixed matrix like this, and then psi j lambda A. It's mixed, but it's actually diagonal in the A index, so it just has one A index instead of two. And the structure of the matrix is W, Ij. This we knew because the conventional fermions have a mass W, Ij times Xij. The mixing comes from a D term. That's because the D term appears in a term that couples gauginos to fermions. Okay, D will multiply gaugino fermions, so it's actually D, A, I appearing here, and here it's D, A, J, and here it's 0. Okay, so the point is that the gauginos don't have a mass matrix with themselves, but they can mix with the fermions. Okay, and this is only M, so it's the mass matrix for the left-handed psi's and lambdas. There will be a corresponding one for the right-handed guys, and if we multiply the two, then we get what we really mean by MF squared. So it's really equal to MF A Ij diagonal A. Or it could be the other way around, and actually we need both, but since we are going to take a trace, we don't have to care, we'll just put a factor of 2. And this thing we can easily work out by taking this and multiplying it as a matrix with its dagger. In fact, I will do, this is what I have in my notes, MF dagger MF. This is W star W Ij. I'm sorry if this is less than clear to read, but then you can find all this. This is, here I'm copying the treatment in DGR's book. It's very easy to pull it out from there. And this much of the calculation I actually did myself. Okay, so it's a 2 by 2 matrix obtained by taking this and multiplying it by its own dagger. Thereby you get W star W, you get D A I bar, D A J, terms like that. And then here you have something complex, here you have its conjugate. I think there's some index. I'm sure there's something I have not done right. I think one of these K's should be a bar, probably this one. Anyway, it won't contribute in the case. So this is the fermion mass matrix, and the last thing remaining is the scalar mass matrix. And then we simply trace them and add them. Or add them and trace them, whichever we feel like. This I'm writing without proof is W star W Ij plus D A I bar D A J plus, here we have to get a new term, D A I bar J, second derivative of D times D. here we have something which I'm not going to bother to write, and here you have W star ij plus dA I bar dAj plus again dA ij bar dA. Okay, we only need those two elements. So it's not implausible, it's just part of the fact that all mass matrices are determined by the superpotential W and the terms because after that's the potential. And now we simply take the super trace. So the super trace m square is the trace of the scalar part minus the trace of mf dagger plus mf dagger mf, which are equal, and plus, since we are now working with massive vector fields, 3 times the trace of the vector mass matrix. Okay, so that contribution gives me 2 trace W star plus 2 dA I bar plus 2 dA I bar dA. So that's the first term. I'll put brackets around so you can see easily what they are. The next term is from here with a minus and a factor of 2 because each of these contributes the same thing. And then I just have to take the trace of that. So I get what happened to the vector mass? Yeah, minus 2 trace W star plus. So here we have 2 and 2 4 inside here. dAi dA. Okay, that's this. So now I can about this since I've taken its trace. And finally I add 3, that guy. The trace of that guy is 2 dAi bar. So everything looks coming along nicely. We see that the W dependence cancels between here and here, which it has to because the vector mass terms don't depend on the superpotential at all. As far as dAi bar, we have 2 here, minus 8 here, and plus 6 here, so they're all gone. And that only leaves behind this term, 2 dAi bar. Okay. And now it's pretty easy to figure out what that means because we already took the d term and differentiated it in I or I bar, but if I differentiate it in I and I bar, the only thing I'm left with is TA. And because I differentiated in I and I bar and then sum over them, I get the trace of TA. Okay. And so this is actually minus 2 trace of TA dA, which I believe is the same as what I found in the special case where I had got minus 2q dA. Q was the charge of a U1 gauge field, so it was the trace of dA. There's probably a G built in here, and I think that's included in the coupling constant. Okay, so we proved our sum rule. Yeah, so that's it. Now, because these terms can be non-zero, it means that the sum rule, the negative constraint for phenomenology that we saw last time may not hold. In other words, it might just be possible with some content of fields to make spontaneous SUSY breaking happen, take advantage of this rule and make everybody all the super partners heavy enough not to conflict with the experiment. But that's easier said than done. In principle, you could probably make a model which did that, but it's not enough for us. We need to make such a model in the standard model or the MSSM field content. Okay, and that will turn out not to be possible. So even this won't really help us. Okay, that in the MSSM, even taking advantage of this violation of the sum rule, we will not be able to. I'll explain that in more detail next time. But even this violation of the sum rule is not useful enough to make a viable, realistic MSSM with spontaneous supersymmetry breaking. As we are phenomenologists, I think I will start using the notation. Is it this way or that way?
It's probably that way because it looks like A star and 60 bar.
Good. So I haven't proved this statement, but I'll just give you a gist of it. This rule applies over the entire theory, right? But supposing you are able to find some rule which is satisfied only in the quark sector or only in the electron sector, that's bad enough. Okay. Even for example, that the splittings in one of the sectors are equal to the splittings in other sector could be bad. Lots of things could be bad. Okay. We see that it's not like the sum rule has gone away just as a controlled violation. There's still a sum rule in operation. So it will turn out to be a bad thing for the standard model, and therefore it is our unfortunate lot that we now have to accept the second most attractive possibility, or perhaps some would call it the least attractive possibility, which is explicit supersymmetry. Now the key point about it is that we'll always be keeping in mind that this is explicit in the sense that we will introduce some terms by hand in the Lagrangian of the MSSM which are not supersymmetric, but they'll be chosen specifically so that they don't destroy the good high energy properties of supersymmetry, and in particular they don't bring back the quadratic divergence in the Higgs sector which we struggled so hard to eliminate. And it will turn out that this is achieved if we do what is called soft supersymmetry breaking, which is that we had a certain class of terms and no others. It's a little bit subtle to define what soft is, but I'll do so in a moment. The other good thing about this, so this is constrained by trying not to spoil the effects of supersymmetry. The converse way about thinking about this is, imagine we have a high scale supersymmetric theory which undergoes spontaneous supersymmetry breaking by some mechanism. How will it influence the effective low energy theory? And turns out that it influences it by introducing explicit soft supersymmetry breaking parameters. Okay? So it's a consistent way to proceed. Instead of abandoning spontaneous supersymmetry breaking, we simply pass it on to some higher level theory. Now, these are all words. I'll have to explain why that is so, and I'll be doing that. As usual, Weinberg's book is very, very good for inspirational, fundamental material of its nature. But we aren't really talking MSSM in today's lecture. We're still talking in the model sense. So I'll complete this lecture by listing for you what are the possible terms that you can add when you want to explicitly break, when you want to break supersymmetry softly. And next time we'll go back to the MSSM, whose supersymmetric sector we've already done, and we'll ask the question: can we implement spontaneous breaking with this sum rule in a realistic way? We'll find the answer to be no, and then we'll say, okay, this is the way to go, and then we'll actually write down what we should write down in the MSSM and see what are its experimental consequences. At the theoretical level, all you need to do is the following. So the first requirement for what is called soft breaking is that all terms have dimension less than or equal to 3, not dimension 4, so they are all super renormalizable. Okay, naively right away that tells you that you expect the terms to be increasingly irrelevant at high energies, okay, which is the whole point. However, that's a necessary but not sufficient condition, because if you introduce certain terms of dimension 3, then under some situations they will generate other terms of dimension 4, and then you'll be in trouble. Okay, so soft means terms with of dimension 3 which are safe in a certain sense, to be made precise. Okay, so let me start by writing out what is the most general L soft. Okay, we assume that our underlying theory has a bunch of chiral multiplets coupled to vector multiplets, and the soft breaking terms are allowed to depend on the ordinary fields, not superfields, contained in those vector and chiral multiplets. Okay. So one example is that we give a new mass term to the scalars in the chiral multiplets. Okay, with an arbitrary mass square matrix that we just took up. Now, it may have been that in some earlier lecture I used this to mean the mass matrix which you get from the supersymmetric sector, but now we'll change the name of that, let's say to mu ij or something, and then these are soft breaking terms. So this is one possible term. Mass terms generally look quite safe. Okay. When it comes to interaction terms, we could think of lots of things, but eventually when the dust settles, you find that the only terms you are allowed, this is a kind of some specific notation which people like to use. Linear, quadratic and cubic terms. Not in the superfield, but in the scalar field. Now you should appreciate that there is a huge difference between this and the things we wrote in a typical superpotential, which also look like this except evaluated on capital phi's. Okay, those were the cubic term was the dimension 4 operator in the physical Lagrangian. Here the cubic term is a genuine dimension 3 operator, cubic coupling among scalars. That's one thing to notice. The second thing to notice is that this is all supposed to be gauge invariant. So of course this won't even be there unless there are some gauge singlet fields and therefore superfields in the theory. But in that case it can be there. Third thing to notice is that here we have deliberately put in only phi's and no phi stars. So there is a plus complex conjugate. But for example, we have banished terms like phi star. Okay, that's a perfectly good cubic term, and classically it is soft, but it turns out that generically it's not soft in the sense that it introduces unwanted dimension 4 terms. These things I'll elaborate on a bit more next time. Okay, so it's amusing that there's a kind of holomorphic requirement, not for the mass term which you're allowed to put in this form, but for the cubic term it has to be phi cubed and not phi star phi squared. It's phi cubed plus phi star cubed, but not phi star phi squared. Okay.
So yes. Mass terms for the fermions?
Yeah, coming up. The next thing we can do is put in a mass term for the gauginose, and that is generally written as minus a half m lambda a plus complex conjugate. So these are Majorana mass terms for the gauginose. Okay. Now the next thing you could ask for are mass terms for the fermions, psi, but it turns out that those also have a danger of not being soft under some circumstances, which I will discuss. I'm still in the process of sorting this out. But there's another nice thing you can realize, which is that if I'm allowed a mass term for phi and also any superpotential, then I can generate a mass term for psi. Okay, because if I have an explicit mass term for psi, I can extend that to a term in the superpotential, which will introduce new mass terms for phi, which I can then remove from here. So it's sort of okay. That's the reason why, the best reason not to introduce psi mass terms. Okay. Very good. Now, actually, we can exploit the fact that some of these interactions look like superfield interactions, to rewrite this as a apparently supersymmetric theory with a fake superfield in it. Okay. The reason is we still want to use superspace Feynman rules to study this theory, but what we have done is to add some new interactions which don't depend on superfields. Okay. So a very nice trick to bring back superfields. Introduce a single new superfield which is a singlet of everything. Chiral superfield called theta, and it's simply equal to theta theta. So its first component is 0, its next component is 0, and its auxiliary field component is 2. So that is equal to theta theta. Okay. Of course, you never say that it's equal to theta theta. You treat it as a superfield in the theory, and somewhere at the end you set it equal to theta theta. Okay, which breaks supersymmetry, but of course we are breaking supersymmetry, so we're not surprised. This thing has a name. It's called spurion. Okay, and what does it do? Well, take that Lagrangian and let's rewrite it as a superspace Lagrangian with the spurion. Very simple. The first term, which is phi star phi type of term. So this is going to be rewritten as a D type of term and these two as F type of terms. So the first term is minus integral d2 theta dagger spurion dagger. This whole thing is 1 times phi I dagger m squared by j e to the v. Okay, so it looks like it's very weird. It looks like an off diagonal kinetic term coupled to the gauge field. Okay, but in this process it's gauge invariant. Okay, and supersymmetry invariant because phi dagger into the v phi is both gauge and supersymmetry invariant. And what will happen when we set the spurion to its true value is that all this stuff cancels out and everything has to be evaluated at its lowest component. But the lowest component is small phi star and small phi, and e to the v, the lowest component is 1 because v's lowest component is 0 in the Western gauge. So we'll just get this back.
But what gives the non-zero f to the theta theta component of eta? That will come.
No, nothing gives it. We just assume it at the end. See, this is explicit supersymmetry breaking, right? So we can't
just say
we can't make explicit breaking back into spontaneous by this. All we've done is postpone the explicit breaking by making a supersymmetric theory in which at some suitably late stage after doing some calculations, we'll set the spurion field equal to that value, which is a non-supersymmetric choice. Okay. So what about the rest of the terms? Pretty easy. We have d2 theta times theta, which is also 1. Then ci phi I minus r pij. So it actually now starts looking like a conventional superpotential, but with the spurion multiplying it. And then the last term is minus a half integral d2 theta raised m wa plus complex term h. So here's the soft, generic soft SUSY breaking Lagrangian written out in terms of superfields, using heavily this spurion as one of the superfields. And it's really trivial in the sense that all of these measures are all one. Okay, so I'll stop there, and I think this concludes the sort of theoretical discussion of supersymmetry breaking of various kinds. I could have gone into days, if not weeks, months and years on dynamical supersymmetry breaking, but I will not. We'll get back to the MSSM from next time and see what we do.
I just want to correct you something I said earlier. I think I was wrong in that discussion on anomalies. I think the charge, the gauge symmetry is really anomalous.
It's really anomalous.
Yeah.
So just QED with a massless chiral
That's
function is anomalous.
It's because
That's what I was wondering.
yes, I think that's true.
I guess the unusual, the reason we never consider it in elementary books is because it's massless and has no interactions. Has no interactions other than the gauge interaction, but still a good theory classically and anomalous one.
Yeah, I think the anomaly Denby variable will be E cube summed over all the chiral functions.
That's right.
And in this case,
Yes, exactly.
it's different in 2 dimensions because you get both chiral and anti-chiral.
Ah, okay.
So I